This is a keyboard where I can press a button and change the layout, or have all the keys go from letters to symbols, or do literally anything you can think of. You could even play a game on it. The possibilities are endless. This is by no means a normal keyboard. These aren't normal key switches, and this isn't a touchscreen. I mean, I can touch it, but that's not how it works. This is a regular keyboard. More technically, it's known as a human interface device. It's one of the only ways you as a human can interact with your computer system. The keyboard really hasn't changed all that much since the days of the early IBM PC when it was more or less standardized to this layout and everyone else just copied Big Blue's homework. While the general layout of the keys in this order has been around since Christopher QWERTY Sholes invented the typewriter, I'm talking about the precise placement of the non-alphanumeric keys around QWERTY that everyone has come to see as the default standard. Of course, if it ain't broke, don't fix it. But what if the keyboard isn't broken, it's just Latin? Every language on Earth that doesn't use or goes beyond the basic 26 letters of the English alphabet has developed a system where this keyboard layout can be used to type their own script. That includes non-phonetic languages as well. This means if your language doesn't use the Latin alphabet, you need to memorize which keys are used to type which letters in your language. As a multi-tongued individual, for years I've dreamed of a keyboard where I can just press a button and it'll change the entire keyboard layout from one language to the next. Or to imagine it in another way to help the Americans stay interested, imagine a keyboard where each key has its own screen. So not only can the layout change between capital and lowercase by pressing the shift key, you could switch between QWERTY, Dvorak, or a completely new made-up layout on the fly. Or have all the function keys be replaced with program launchers, or turn your number pad into a soundboard, in addition to being able to set the keyboard font and colors or just replace the keys with images or animations. There are no real limits as to what a customizable keyboard like that could do. Well, isn't that just like a digital keyboard on your phone? You can do multilingual input, and you can do all that fancy layout stuff. I could just hook up a tablet to my computer and get everything I want, with the only downside being that I'd be typing on a tablet all the time when I'd rather type on a bed of nails. I wouldn't call myself a keyboard head, but I do appreciate the feeling of a satisfying key press. What I'm looking for then is a keyboard where some kind of physical keys all have their own digital screen. There are plenty of keyboards like that, or should I say there were plenty of keyboards like that, since nearly every one of them has been a commercial failure. Take for example the Optimus Maximus keyboard, released in 2007 at the whopping price of over $1,500, which I'm guessing stems from the price of the 113 individual OLED screens. Even the spacebar gets a single tiny 48 by 48 pixel screen. I would be very happy with a keyboard like that, but it was discontinued and later replaced by the Optimus Popularis in 2012, which was only about $1,000. This keyboard ditched the individual screens for a single LED panel underneath a bunch of transparent keys, and that has pretty much been the go-to standard for keyboards with digital keys ever since. It's just much more cost-effective than buying hundreds of tiny individual LED panels. Plus, if you're smart about it, then you can actually get more pixels per key, and you can use the space between the keys as well. Since then, whether it's been an e-paper version, the Stream Deck, or even a newcomer like the DS Pixel keyboard, it's been the same formula of screen underneath with some kind of keys on top. But that's where the real differences come into play, because a lot of these keyboards just use a touchscreen and some kind of plasticky capacitive key membrane they throw on top, and that's just typing on a tablet with extra steps. As of today, the product that comes the closest to fitting all my needs is the Flux keyboard, which is supposedly shipping out in only a matter of weeks at this point. However, this device only meets 60% of my needs since it's only available as a 60% keyboard, but I need nearly all 104 keys. Besides requiring a number pad to function properly, I'm a profound user of the keys on this island here, to the point where when I'm on the go, I use an auto hotkey script to change my laptop's disgusting media keys into the page up, page down, home, and end keys. The keyboard design itself can be broken into a layer of transparent keys on top, then a screen in the middle, and a layer of electronic components beneath that to detect the key presses, which will be connected to the brains of the keyboard that will run both the key press detection code, the keyboard graphics, and send any keyboard inputs onto my computer. But since even transparent key switches would obscure the screen underneath, the first and hardest question is, how do I create completely clear and wireless key switches? Lasers. I could have a matrix of lasers that will be able to detect when a key has been lowered, similar to the way a regular keyboard matrix works, except that if the keys are transparent, will the laser just go through the key? And how do the keys manage to spring back up? Anti-gravity lasers. Aw, Kickstarter? I don't have time for that. Forget the lasers. Magnets. If I slip in a magnet, or even a couple magnets, between the screen layer and detection layer, that may be enough force to push the key upwards and keep it in the air. Then I can have a Hall effect sensor underneath to detect the strength of the magnetic field. When you press down, the field gets strong enough that it will trigger a key press, which can be handled by the controller and sent to the computer. Before getting into the design of the keys themselves, I've already scoped out a 1440p LED screen which has a 6mm thick back panel, which is about as thin and as high resolution as I can get without breaking the bank. And while the screen's 16:9 ratio isn't the optimal size for a keyboard, I'll just have to keep everything on the bottom and be left with some space on the top I can fill with graphics or something. Anyways, let's hit the catwalk and start modeling. Above the electrical components to detect the key presses will be a layer of repelling magnets. Then there is a 6mm gap for where the screen will be, and the keys will have a standard travel distance of 4mm, plus each key has a 1.5mm serif edge to keep it from falling out of its socket, and this defines the distance between the bottom magnets and the bottom of the keyboard shell. For testing, I've created this model which holds up to 4 keys at a time. At this stage, I'm trying to determine how many magnets to use to make it feel like it has an equivalent resistance to a typical key, and in what orientation those magnets should be laid out. This model has 2, 3, 4, and 1 magnet slots in both the base and the keys themselves, but I'm also trying out multiple different kinds of magnets. These are all sold as N52 grade neodymium magnets. The box they shipped in said N50. But either way, these are around the top end in terms of magnetic strength you can get commercially available for cheap. Ideal for me since I'm going to be buying hundreds of them. These magnets have different diameters and thicknesses, but in my 3D model I have a variable set up for those measurements, so I just need to replace those values and my model will automatically update itself, and then I can export and print all 3 versions of it. That's why parametric modeling is so cool. Pressing them, I'm trying to get a feel for both whether the resistance of the key is good, but also if the key feels stable. Surprisingly, the keys supported by both 3 and 4 magnets feel very wobbly. I think it must be because the magnets are positioned so that the keycaps tend to want to move into the corner. 2 and 1 both feel decently stable, with 2 feeling just a bit better overall. As for which strength of magnets to go for, the smallest magnets are honestly too weak for me. I really like to smack the keys around when I type, but the largest magnets may just be a wee bit on the strong side. Combining the thick magnets in the keys and a thin magnet plate underneath is about the level of resistance I'm looking for, but it still feels a bit off. They feel like you're typing on a cushion or something. It doesn't feel satisfying at all, but I think there might be a better method. By moving these supporting magnets into the top structure and shifting the 2 magnets from the bottom of the key onto each side, it creates a sort of magnetic skewer that has more than enough force to pull the key into the upright position after being pressed down. In this model, I've used thick magnets in the frame walls and thin magnets in the keys themselves, and they feel much smoother than the first prototype. I think it's that thanks to the inverse square law. In the first model, as you press down, there was exponentially more resistance. But in this version, the highest resistance to overcome is in the initial press, with it getting exponentially easier as it gets further away, creating a much more satisfying key press. This is also how the keys in the Flex keyboard work, though I swear I only figured that out after I had this prototype finished. And I understand why they used this method. It actually feels really good to type on, like poking a ripe avocado or pressing on a mechanical key. As a bonus, this design no longer requires that layer of repelling magnets between the screen and the all-important detection layer, which will be a PCB with a bunch of Hall effect sensors on it. As the name would suggest, these components are able to detect the magnetic field around them through the Hall effect, and then output this measurement as an analog value. Since the magnetic flux density of the magnets I'm using are all relatively low, I need a pretty sensitive Hall effect sensor, such as this one, which will output 9 megavolts for every 1 Gauss it detects. In a traditional keyboard circuit, Each key isn't directly tied to its own output signal, there's just too many keys and not enough output pins, so that's why a keyboard matrix is used. But in my keyboard, each key needs its own personal Hall effect sensor, so there needs to be a way to read the value of each key's output independently and on demand. Let's take just the number pad as an example. Each Hall effect sensor will be hooked up to 5 volts and ground, and the analog output will be fed into an analog to digital converter, which will measure the Hall effect sensor's output voltage against a reference voltage and output a binary number which represents the key's current output value. Instead of one ADC per key, I can use an ADC multiplexer like the MCP3008 to group 8 signals together. 2 of these is one less than the 17 keys on the number pad, so I'll just drop a key for now. And with the ADC multiplexer, there are now only 2 output lines, but these can actually be tied to the same line since it will communicate with the keyboard controller over serial peripheral interface, using 4 total signals: data in, data out, clock, and chip select. Only when the chip select line is active will the ADC output one of the 8 key values. For the number pad, I only need 2 I/O lines, but with 104 keys, that's 13 different signals. And rather than 13 individual wires, I can reduce it to only 4 using 2 3 to 8 pin decoders. Again, just looking at the number pad for now. With only 1 I/O line, the 3 to 8 decoder will change which of the 2 chip select lines are selected based on this 0 or 1 value. Expanding outwards, with 2 3 to 8 decoders and 4 I/O lines to represent a binary selection from 0 to 12, I can read the value of any ADC chip on command with only the 3 SPI signals, 4 I/O lines, and of course power and ground. At least that's how it all works in theory. I don't want to produce the whole PCB at once in case I made some kind of error here, so I'm only going to produce a number pad prototype first. Same with the keys themselves. I only want to make the 17 number pad keys and top part of the frame for the first trial run. Material-wise, to create completely transparent keys, pretty much the only option available is 3D printing in transparent resin. But since I don't have a resin printer and I'm not going to become a resin YouTuber to justify the investment into all that equipment, I can still get these models produced through the longtime channel sponsor, PCBWay. There are a ton of really cool non-standard 3D printing materials you can choose from after you upload your model to their site. I'm desperately trying to find an excuse to print something out of steel or titanium, but I do have to stick with transparent resin for my keys and shell today. At the same time, I can upload my PCB and bill of materials through their assembly service. Then they'll order the components for me and solder it all together, which is great for an amateur like myself who knows how to solder but not well and doesn't have the skills needed for surface mount components, especially later on in my final design when the keyboard will have hundreds of tiny capacitors and resistors. Even if they weren't sponsoring this video, I'd still recommend them, so check them out through the link down below for all your PCB, 3D printing, and other manufacturing needs. And while those parts are off being manufactured, I have some time to focus on the programming side of things. It's really the software that will be the defining factor in whether this keyboard is any good or not. A traditional keyboard really doesn't need anything more than your basic $2 microcontroller to manage the simple key matrix. But my keyboard will also have a 1440p screen, and so meets the rare requirement of actually needing a single board computer like a Raspberry Pi. But still not a Raspberry Pi. I'm going with the Orange Pi 5. Mine happens to be the Ultra version, but they're all pretty much the same with a Rockchip RK3588 SoC, which has a built-in graphics processing unit. That's the main reason I chose this board over the Raspberry Pi 5, since in comparison the Orange Pi 5 is a little weaker in terms of single-core performance, but makes up for it in multi-core and GPU-heavy workloads. And since I'm building a multi-threaded GPU-heavy program, this is the ideal board for me. But this thing does get extremely hot. I don't have a thermal camera, so here's an artistic rendition of how hot it gets when it's working. Yeah, it's cooking. Not being as popular as Team Raspberry, Team Orange doesn't have as much written support out there on the internet. So while some things like figuring out how the wiring Pi library to interact with the GPIO pins were pretty easy to figure out, it took me a nearly whole day banging around inside of the system and 4 separate Linux installs before I figured out how to enable SPI on the board. Turns out it was in the manual the whole time. Eventually, I wound up right where I started, on Orange Pi OS, which is pretty much Arch Linux with just enough drivers to get the Orange Pi up and running. Luckily, it didn't take too long for my first batch of hardware to come back from PCBWay, so here it is after I took some time to install the magnets into the frame and the keys. Some of these are a little tight due to the type of resin used here not being meant for precision parts. I could edit my model to make it a little better, but it's really not meant for things this small. Some of these keys feel very good to type on. Others are a bit too snug, but I bet sanding it down would make them slide a little easier. And the PCBs look great. Very cool to see everything put together so nicely. And the I/O pins are all ready, so I just need to wire everything up and I can start reading out data from these Hall effect sensors. The only thing I left out about the output process before was how to select which of the 8 Hall effect sensors connected to each ADC to read from. That comes down to SPI being a two-way communication interface. After resetting the chip select signal, the MCP3008 waits for the SPI data inline to send a 1-bit, which signifies the start. Then I'll send another 1 to specify that I want a direct read from the selected sensor, and the next 3 bits represent which sensor to read from 0 to 7. After which the chip responds on the data outline with a binary number from 0 to 1023. I've whipped up this program that allows me to say read sensor 0 or read sensor 15 and then print the output. So I should be able to see a clear change in the output by moving around this magnet near the sensor. And there we go, that's really cool. It looks like it's working perfectly, and since I know that there's going to be about a 3 to 4 week lead time on my final PCB component and assembly due to the complexity of everything, I'm going to roll the dice a bit here and scale up the PCB design and the 3D model to the full keyboard, and get that order in right now, well at least as soon as I make a few changes. First, I don't like how these keys have really long legs inside to house the side magnets. Since it's transparent, you can see that most of this material isn't needed, and it just blocks the view. So instead, I'm going to increase the thickness of the sidewall, which will make things hopefully look less cluttered. But I can also slightly increase the size of the keys by shrinking the vertical bars between them from 2mm to 1mm. That means I have to use thin magnets instead of thick magnets, but this model shows that it honestly feels the same. Even the spacebar isn't having many issues. In fact, considering the original models again, maybe I went a bit overboard on the resistance with the thick magnets. The keyboard's top frame also has a bunch of blank space at the top, because again 16:9 isn't a good size for a keyboard. So instead of a solid block of costly resin, I hollowed most of it out. With the PCB fully scaled up now, I also decided to add an extra layer of function keys on top. That's how you know your keyboard means serious business. The total part count on this is now exactly 500 individual components, and I think I got a lot better at laying tracks by the end of this hours-long process, but I'd rather not try to untangle my mess from the beginning, so I'm just going to assume it'll be okay. So let's just send that order off and hope for the best. Finally, it's time to start programming in the environment people always tell you is better than your current setup, a basically blank install of Arch Linux. So, where to start? Graphics, I guess. How do graphics work? So I can use SDL2 to create a window, then initialize an OpenGL rendering pipeline and write vertex and fragment shaders in OpenGL shader language to render triangles, do some classic color experiments, and then throw textures on the triangles. There we go. OpenGL coordinates have 0, 0 at the exact center of the window, with -1, 1 being the top left, and 1, -1 being the bottom right, and so on. The screen is 2560 by 1440, so it takes some basic math to create a function that says draw a box of this color at this screen coordinate here, convert it into 2 triangles with OpenGL coordinates, and throw them into the rendering pipeline. And if that's possible, so is drawing images and circles, which covers 100% of a regular keyboard layout, but barely scratching the surface of what's possible. Text can be rendered to the scene by using SDL to turn a string with an attached font into a surface, which can be turned into an OpenGL texture and shoved into VRAM with the rest of the resources. This turns the text into a static image that can be changed since it was pre-rendered, but that's alright since the letters on your keyboard don't change. But for debugging and potentially other situations, I want dynamic text so that I can change it on the fly, but that means I need a set of pre-rendered ASCII characters and a static image file, so better not to use a dumb font like Comic Sans. I'll stick with the sophistication of Papyrus. Then with a text object that has a location, size, color, and string, I can feed in the letters one by one into the rendering pipeline while using a shader that will base the texture coordinates off the ASCII value of the given letter. So if the text object string changes between frames, then on the next render it will be the new letters that are drawn onto the screen, and thus the frame counter is born. Earlier I was joking about Papyrus. I really intended to use this 7-segment font for most things, but it turns out that 7-segment letters are a joke, so I actually did wind up with Papyrus as the default font I used most of the time. With the basic graphics figured out, I defined where each key on the screen was located. At the current size of the keys, each one has about a 96 by 96 pixel area all to itself. I've written some code to abstract everything so that I can say draw a black rectangle on key number 3, draw this image on key 9, or draw a red circle on key 14 and fill it with the text.
That was easy.
To make things even simpler, I created a function so that on load the program will open and parse a keyboard layout profile, which contains a list of functions and parameter values that will build a certain layout, such as the Western or the Math major. And since this profile also defines the output value for the key, the modern student is a legitimate profile I know at least one of you is now desperate to have. The layout profile can also provide custom shaders, including a key pressed shader, to use only when the key is pressed. For now, my basic press shader just inverts the key's associated texture, but the possibilities are as endless as shaders themselves. After the initial profile load, my program was split into 2 threads. One that will read the status of the key's Hall effect sensors, and another that renders the graphics. Each key's Hall effect value from 0 to 1023 is displayed as dynamic text over each key so I can see what's happening. And it's not really working. Something is really wrong with my press detection here. Every time you see it light up in teal, that's when it detects that a key is being pressed. So I really need to rethink what the output value actually means for the keys. The current polling algorithm is simply checking the value of each key's Hall effect sensor and measures it against the static threshold. And due to the orientation of my current magnet setup, any values below this threshold are considered a key press. And actually, the Hall effect sensors are contributing to this issue. Hall effect sensors are most effective when tangent to the southern pole of the magnet, which these magnets in the sides of the keys are not. They're parallel. So when the key is pressed, I'm only measuring a minimal change in the Hall effect sensor's output, like 20 or 30 points difference. Now I could change out the surface mount Hall effect sensors for the through-hole version, which would make the orientation of my current keys correct, but I already ordered the final PCB with the surface mount versions, so I need to make this work. Luckily, I'm not a total fool. I knew this might be an issue, so I created the fail-safe in the bottom of the keys. This little circle here is just big enough to slip in another magnet, which maxes out the Hall effect sensor when right up next to it, but with the screen in the middle, I get a difference of a few hundred points between the top position and bottom position of the keys. Unfortunately, and I don't know which side of my family it's from, I do have some fool's blood in me, because I didn't include the fail-safe hole on the foot of the hundreds of keys I already ordered for the final keyboard. So it's going to be an absolute pain to find some way to slip in a tiny magnet into the bottom of those keys. But I'll cross that bridge when I get to it. Still, this new magnet doesn't help with any of the noise present when polling the keys. Sometimes it's in the range of 100 points or more, causing sporadic key presses. But in general, this noise appears to affect all the keys in the same way at the same time, which is good because that means that hopefully it can be filtered out. As a first attempt, for a second or two after the program is initialized, all the keys' current values can be summed and averaged to create a more accurate threshold value, replacing my initial default guess. Then, by taking the average of each key's value over some number of their pollings, the key's output value should be rid of any outlier values. But while these improvements have gotten rid of some of the individual spikes causing key presses, the Hall effect sensors are still subject to global noise. So instead of creating slices of time and averaging those values, a rolling average can be created by throwing out the top of a list of recent values when new data is input. Then all the current key averages can be used to create a global keyboard average, which should represent the state of the majority of keys at that point in time, which, unless you're a StarCraft player, is usually unpressed. This value can't be the exact threshold to compare to, otherwise about half the keys at any point in time would be counted as pressed. Rather, it's the outliers to this value that represent a pressed key. So by comparing to below 100 points less than this global average, with most key presses going between 150 and 300 points less than this average, it should be pretty clear as to which keys are being pressed. Well, mostly. Since there are only 16 keys, then a single key going low by 300 points can really throw off the global average, but hopefully with 112 keys, this system will work much better. Plus, there is some noise coming from the other cables running by the I/O wires right now, but in the final case, these will all be far away. Also, I haven't mentioned this earlier, but I took off the front of this panel earlier. I would have taken the entire panel out, but they used a bunch of glue and I didn't want to deal with it. So it is how it is. I swear I'll be debugging C++ for what feels like a second and suddenly a month has passed. Alright, a bunch of little pouches. Glad no one at the post office opened this one up. The PCB looks brilliant. You can see here we have the MCP3008 chips, and then we have the two 3-to-8 decoders, and the 112 Hall effect sensors, and I even managed to add a little Inkbox logo over here. And here's the keyboard frame. Oh, that looks absolutely incredible. And these are the keys. They look great too. And that's a lot of keys. Test fitting these, they fit mostly well. Some things seem to be a bit tight, but nothing a little sandpaper I'm sure won't fix. But first I have to glue 2 magnets into the side of each of the over 100 keys, plus the other hundreds of magnets into the frame itself. That's a lot of magnets. 2 big problems here. 1, the keys are definitely too tight. I can hardly push some of them down. Typing is just not possible. But when I went to go and sand the keys, I couldn't take off enough material to have the keys slide in and out easily without cutting into the magnet holes. Plus, remember how I said I would have to find some way to put a magnet into the base of this key? Well, these are incredibly small and difficult to hold, so without a hole on the bottom, there's just no way that I'm going to be able to install all 112 foot magnets. So this means I do have to redesign the keys to be a bit smaller and then add the hole in the foot for the bottom magnet. That means another 2 to 3 week manufacturing delay because there are 125 individual parts, including the spare keys, that need to be printed and then polished by hand. So big apology to the poor guy whose job it was to polish my 250 keys. Okay, so here's the wedge case I made in Onshape. So let's wire this up and put everything in place. There's no need to place the keys on top yet because I need to make sure all the Hall effect sensors are working correctly. I've already adjusted things to display all 112 keys on the screen, so all I have to do is run the program, and it crashed. Oh, I hope that was a fluke. Please let that be a fluke. But he knew it wasn't a fluke. He spent the next 8 hours of his life trying to debug himself out of the worst series of crashes he'd ever seen. Certain logs revealed that the HDMI input signal may be the main culprit, but there was no way to turn it off except through directly editing the device tree below. He had to decompile the device's specific DTB file, disable HDMI RX, and recompile. He had slogged through hours of pain and frustration, only for success to have been 8 bytes of change away the whole time. 8 bytes. That's one double precision floating point, almost half an SHA-1 hash. Are you kidding me? Still? I don't get it. I leave the PCB unplugged and the program works fine. I plug it in and it always crashes. Is my PCB the problem? I don't think so. I wrote a test program that reads all 112 sensors without any issues at all, and it seems to be even more stable than my number pad version. So what could it be? It turns out to have been a political issue, because it came down to something orange wanting more power. I had been running the computer off one of my PC's USB-C ports, but I remembered that the Orange Pi is actually pretty finicky when it comes to power. It's recommended to use a 5V 4A power supply that's above typical amperage. So once I changed to getting the juice directly from the wall, the program worked flawlessly. I'm not going to roll back my HDMI RX changes because it did get more stable after that. I don't know what that's all about, but as you can see now, everything is okay. Every Hall effect sensor is working without any problems, and the press detection method from earlier is working really great as well. You can see that even just a quick key press will easily be detected. And since I'm still waiting for the new keys, I should probably finish my software, starting with making sure this Bluetooth keyboard actually has Bluetooth. How does Bluetooth work? Whoa, that's crazy. How did he unite Denmark with this? Bluetooth isn't all that different from traditional networking, but it's not as easy as just creating a client and a host. Bluetooth terminology is a bit different because it is just a bit different. You have central devices, which are similar to clients, that connect to peripherals, which provide data and services, such as a keyboard or a speaker. Like TCP/IP, Bluetooth is a two-way communication channel, but you can't throw raw bytes down the line like with serial. It has to come in a particular format. In the case of a human interface device, the peripheral sends standard HID reports, which consist of a lot of metadata plus one tiny section that actually matters, which keys are pressed, up to 6, and which modification keys are being held. With that high-level overview, you'd think by now some lonely developer out there would have created a robust library to, as a peripheral device, create a Bluetooth advertisement, set its properties, connect to a central device, and send a couple of HID reports over. But no. There are the basic Linux libraries for Bluetooth, but nowadays it's recommended to use dbus to talk to the system's Bluetooth hardware. But all of that is extremely abstract and would take me literally weeks to set up properly. So instead, I only spent days trying to figure out some library to make Bluetooth communications simple and easy, and just when I think I would have found something that worked, it turns out it was always just another library to create a central device to receive Bluetooth notifications. Programming is sometimes like searching for the magic words to get the computer to do the thing you want. You know it's possible, the hardware is all there, you just don't know the combination of letters that you need to make it do the thing. On the entire internet, there was only one guy, Hedgehog, who said he ran into the same issue with Bluetooth libraries and took a few weeks to put together a script to create a Bluetooth peripheral and send a single key press report over to a connected device. I ran it, and it worked. The only problem is that he wrote the thing in Python. No hate to Python here, it's everything Java ever promised it would be. But I'm a man, and men only program in C++, and that's only if the time constraints don't allow me to program in raw assembly without an operating system. But I'm going to have to put my differences aside in the spirit of cooperation to create a workaround held together with gum, paperclips, and interprocess messaging. Using a library available in both C++ and Python called ZMQ, I can create a TCP socket from my C++ program over to my Python program. When a key is pressed, the key info can be added to a message buffer which will be sent through the socket onto the Python program. There, the data from the message can be extracted and sent to the central device. For efficiency, I can add another thread to my program to manage the output queue, in addition to the Python program also running at the same time to manage the Bluetooth connection. Right now, I still have to go into Bluetooth control on my Orange Pi and manually set the advertisement to on and set the appearance to be a keyboard before it'll appear on my PC for me to connect to, but once I do, I'm actually able to send key data from my C++ program to the Python program through Bluetooth onto my computer. That's all great, but until now, I've only been able to draw simple shapes and images onto the screen, and cool shaders are only able to take me so far. This is a Quad HD screen after all, so why not play some high quality HD video on it? Except since this is my own custom graphics engine running, how do I play video on it? There's no simple STL or OpenGL function to play a video, so if I want it, I'll have to decode it myself. Now, I don't mean dealing with the P-frames and I-frames directly. I have a special project in the works talking about those things, so you'll just have to subscribe and stay tuned for that. Right now, I don't have to worry about any of the actual decoding details because all I need is FFmpeg. Let me clarify how to use this here, because I read some online tutorials that got it wrong and it threw me off for a long time until I checked the documentation. When you want to decode a video, you need to initialize FFmpeg, including the file location of the video you want to play. This starts another process in the background that you need to communicate with. So you locate the video stream, then start getting the frame data packets from it. These packets need to be sent to the AV codec to decode the data into a regular image. But the codec might come back saying that there wasn't enough data. So the important part is right here. Send the same packet back. Don't send the next packet, just the same one, over and over if needed until it comes back with the frame image. Then you can move on by sending the next packet in line. But before that, take the image that you just got, you might have to convert it to RGB if it's in another color format, then stick it in VRAM as a texture and render it on a quad. That's one frame of video. Decode the next frame, but don't stick it in another place in VRAM, just replace the current frame data, then it'll show the second frame. Decode and replace your frames at whatever timing your video is at, grab some popcorn, and that's video at home without spending all that money you would have at the theater. To avoid stutters, create a buffer of frames so that when you get to a particularly hard to decode frame, hey, get out of here, you can rely on the buffer to give you some cushion time. In my program, the video is decoded in an independent thread split off from the graphics thread, so you can see why it was important to have an SBC with great multi-threaded efficiency. I would say this is pretty crazy, but you could just open the video file and play it in any old app. But it is cool that it's playing in my own program. Still, for some reason it's having some issues creating these visual glitches. I think that's a problem with the decoding part of things, but I'm relying on FFmpeg, so I don't know what that's about. Either way, it's good enough for me. Oh, the final box is here. Alright, it's going to be another long session of gluing. Fortunately, there were less than 300 keys in this entire project, and at 2 magnets per key plus the magnets in the key frames, it was less than 1,000 magnets that I had to glue in over the course of this project, so not too bad. I did drop this top shell by accident and I cracked the corner and a couple of these branches between the keys snapped as well. Luckily nothing was beyond repair, but I still feel terrible about it. Let's throw it together. Time to boot it up. Very cool to see it all coming together. Let's press a couple of these keys. Oh, that feels great. Really accurate with the key press detection here. Let's finally connect this to my computer and do some typing. Let's try hello world. Well, the polling code seems to be working, but it's having some issues with the Bluetooth output side of things. So, it was my understanding that once a key was pressed, you were supposed to just spam as many messages as possible through Bluetooth to the computer, but that's not exactly how it works. Rather, you're supposed to send one message when a key is pressed and another blank message when the key is released. Then it's up to the OS to determine which key statuses have been changed by looking at the differences between the messages. With this new method, let's try typing again. Show me hello world. Okay, that's better than before, but now I'm getting double letters. I don't know why. I'm only sending a single message. I'm absolutely sure of that. Okay, I fixed it. Kind of. For some reason, when the report sends only one key code, it outputs only one key press. But if I increase the number of keys in the report to more than one, it will output a double key press. I know I'm setting the size correctly in the HID report because it just doesn't work if the size is wrong. No keys get output. I don't know what the issue is here, so I'm kind of stuck with only one key able to be pressed at a time, and that's just going to be good enough for me right now. It's time to see what this keyboard can do. I've changed this top row here from function keys to layout transition keys, so I can swap from regular English to Khmer, to Chinese Sangye input, to Japanese, to Dvorak, and again, if it wasn't clear, this actually remaps the keys so you can output all E's if you want to, and this literally types only E's. How about a couple of theme keyboards like the fishbowl, world time zones, or the please don't sue me? And here are a couple of layouts I came up with based on sections from Unicode. Mahjong tiles, enclosed CJK letters and months, and Egyptian hieroglyphics. But because this thing is an actual keyboard, I can only send the letters and keys supported by HID reports. So even though there are actual Unicode code points for all these symbols, I can't output them directly to the computer. I'd have to rely on software on the receiving PC side of things in order to make it work. But that doesn't stop me from creating layouts for keyboard shortcuts for Photoshop or Minecraft. And I think the only appropriate thing to do now is a typing test. I I dare you to beat that score. Okay, so it's not a great keyboard. The keys are actually a bit on the small side after the reorder, so they shift around in their slots a little. That makes them a bit wobbly, and the space key in particular is very unsteady. I think a nice redesign would be to actually remove the bottom key serif entirely and not have the keys be quite so tall. Then even the travel distance of the keys could go down a little bit, creating a much flatter type of keyboard, one that wouldn't obstruct the view from the sides too much. Software-wise, everything worked out except for the multiple key presses at once, but I'm sure I'll be able to figure that out soon, as well as maybe doing something for Unicode output later on. But to look at this thing and think that I literally built a working keyboard from scratch, and not even a regular keyboard with wireless keys, but one with a custom GUI, that's pretty incredible. Everything in this project is open source, so feel free to check out that GitHub repository if you want to build your own. And I know this video took an extraordinarily long time to finish, but what can I say? It took a lot of work, and I really do think it was all worth it. And while I can never promise daily or even weekly uploads, I do want to try to balance out these larger projects with some smaller ones. That being said, I've launched a Patreon if you'd like to more closely follow along and help support my work directly. YouTube has been my biggest passion for a couple of years now, and I hope to continue this work for many years to come, and your support is a big part of that. So genuinely, thank you for watching.
I love magnets. I just don't know how they work.